next speaker, Guillermo Garcia-Segura, who only ever addresses the difficult questions, will talk about common envelope shaping. Guillermo, you might still be muted.
Here, welcome. Hello everybody. It's nice to be back in Granada, which is my first alma mater. This is a nice collaboration with Paul Ricker and Ronald Taam, both from Illinois. So we agree more or less right now that rotating single star cannot form bipolar planetary nebulae. So the way how we are working now is trying to redistribute all the gas to the equator by common envelope evolution. You know, for a common evolution, first you start with a Roche-Low overflow, then you go to a Roche-Low overflow phase, then you come into the common envelope evolution, and then after that, a self-regulated phase where a circumbinary disk form. This is the place where we are going to start doing our models. So the first part of the talk is going to be assume that the primary star is hot enough to produce a line-driven wind. This is the first work that we did in 2018. So we took the 3D flash computation by Paul Ricker and Ronald Taam. We had to do it in 2 dimensions because the evolution time is quite large. We cannot do in 3D. And also we need to change our grid from 10 to the 13 centimeter to 10 to the 18, so it's 5 orders of magnitude. This is hard to do in 3D. But in 2D it's very easy because we can expand the grid in spherical coordinates. So basically we put here the light-driven solution, for example, the one by Basiliadis and Wood, like for 1 solar mass or 2.5 solar masses. And at the outer boundary we put the RGB. Sorry, shut up. So we have a problem here in house with all the noise. So it doesn't matter what kind of light-driven wind you put here, because at the end you always get a bipolar nebula, either for a red giant star, for an AGB star of 1 solar mass, or for 2.5 solar masses. So what we found from this study very quickly is that you can form multiple bipolar, multiple lobes in general, and these multi-lobes are formed by photo evaporation. For example, in the case of this IFAS nebula, it's really nice that this is a eclipsing binary with 8 hours, so there is no doubt that this is a compact binary. So the key here is that you have too much mass in the equator right now, so you can photoevaporate this gas and form a photoevaporated wind which collide with the line-driven wind. So these form inner lobes, either bipolar or spheric or elliptical. So. The second part of the talk, I don't have time to do this, so you can go and read the paper, but I'm going to skip this part and I will go direct to the third part, which is the most, I think, more interesting right now, which is the launching of jets and magnetic winds in these solutions. So again, we start with the 3D flash computation. The computation doesn't include magnetic field, but we did just an approximation of including a toroidal field. The toroidal field that we include is very small compared to the equilibrium, to the equipartition value. We just use 5% of the equipartition value with a maximum of 500 Gauss over here. We check this with MESA and the binary evolution code to see what kind of magnetic field produced the star in the transition between the core and the envelope. So this is of the order of the magnetic field that we are getting. Of course, inside the star, most of the magnetic field is toroidal. So in the ejecta of the envelope, most of the magnetic field is going to be also toroidal. You have poloidal field also, but I mean, this approximation we use only here toroidal field. So once that you form the circumbinary disk, that the gas that is compressed here also compress the magnetic field. So when we had before 500 Gauss, we get now 15,000 Gauss. So 10 to the 4 Gauss is a very important magnetic field to start with this. I mean, this is not, for example, you don't have this situation in star formation, but here we start already with big magnetic fields. So, but it doesn't matter what I mean, in this model, if you run this model for a long time, many years, nothing is going to happen because the toroidal field in 2 dimensions is stable. There is no practically, the gas is going to be in Keplerian orbit, nothing is going to collapse. So to do the collapse of the disk or the accretion, we need to create a poloidal field. And the way that we create the poloidal field is from the toroidal field. We know the fields are unstable to many things like turbulence, convection, Parker instability, magnetic buoyancy. So we are assuming that the toroidal field is going to be perturbed and it's going to form up and down magnetic field above the disk and below the disk. So that's the way that we get the poloidal field. And this is similar to the Blanford-Payne solution, but instead of the radial direction, we have the phi direction. So this is the way that we produce the field. Now we have the R component, R theta and phi, so the R, the beta component, the theta component, and the phi. So we have a poloidal field and a toroidal field, which the toroidal field is more important in magnitude. So this is the first solution that we did. This is our binary star is here with a period of 2 days. And what you are going to see is just gravity here. We don't put any injection of mass loss, momentum, energy, I mean, just gravity. So this is the way how evolved the system. Now with the poloidal field, it start to collapse, it's getting sub-Keplerian, it's not in Keplerian orbit anymore, and start to compress the gas near the binary, and also start to enhance the magnetic pressure there. And the launching of this wing is by magnetic pressure, like a magnetic tower. Also, when the mass loss, the mass accretion rate is too important, it cannot handle more accretion, so it start to produce what is called a plasma gun at the pole and produces small jets. So the solution basically is a white jet here, and I'm going to stop it here. We have first a magnetic tower, which is like a X-wing in shape. Then we have these thin, narrow jets, very fast, and at the end we have some kind of white jet. So what is happening here is that the system, the binary system, produces a gap, and that gap over here is a very important centrifugal barrier. So when you have this barrier, and you think that this is like a piston, when you compress that gas, the piston forms the gas and the centrifugal barrier is forcing the wind to go to the polar direction, also accreting to the binary as well. So basically we have here you see that is subalbenic, the ejection is by magnetic pressure. We have some co-rotation in the V5. This is the radial velocity. This is where all the launching is done. So at the end of the simulation, we get a mass loss rate of 10 to the minus 7 and a mass accretion rate of 10 to the minus 5. This is supersonic and superalbenic over here and subalbenic here. This is the history of the mass accretion rate. It's bumpy. You see that it's not steady, as well as the mass loss rate. And the solution of the white jet is similar to a tapered flow that Bruce Balick is using in his calculation. So this is a confirmation of that. I'm not going to talk about the small jet, but you can see here how we can follow the jet. And it's very fast. The narrow jet up to 3,000 kilometers per second. You can read in the paper with more detail. So now we are going to see what kind of nebula produce this computed wind. If now we insert the computed wind in the ejecta of the Paul-Ricoeur computation, we introduce here as an inner boundary condition the magnetic wind. And this is what you form, a very nice bipolar nebula. Well, it's a protoplanetary nebula, actually. I have two minutes more, I think. So we were playing with several solutions, different mass loss rate, different way to treat the magnetic field in the outflow also. So comparing with real observations, with real object, for example, W43A is a water fountain. I think it's the best case right now in protoplanetary. You see the jet in CO very clearly, the bipolar lobes here. The agreement is, this is 50 years, 60 years, but I mean, it's amazing. Now the other nice agreement is, for example, with the Calabash Nebula. We can see here the fish bowls, the reverse shock here, actually the shape is similar. It's very hot here, you form H alpha here, as you see in blue. The solution is very cold, so it's molecular gas here in CO. So now this is the second solution. The period is 5 days, is wider now. So again, this is only gravity. We don't inject any injection of energy or momentum. So the escape velocity here of the system is smaller, so the wind also has a smaller velocity. Produce also a magnetic tower in the form of X-wind, but it's much slower, like 30 kilometers per second instead of 250 kilometers per second. Also is produced when you have too much accretion, you break the barrier, the centrifugal barrier in the polar direction for a narrow jet here in the polar direction. So we now study this kind of wind to see, I mean, we put in the ejecta to see what kind of nebula produce, what kind of protoplanetary nebula. And now the solutions are more elliptical, also with the ansai and the jets in the polar direction. And when you treat the magnetic field that because of instability, like the King instability or whatever, so you have a more ballistic flow, and you produce this kind of shapes like quadrupolar, or maybe in 3 dimensions are like starfish. We have to do that in 3 dimensions. So I think with this model you can explain this kind. This is the future project is to produce the planetary nebula that is coming from this protoplanetary nebula. So I think I can end here. Thank you.
Thank you, Guillermo. Are there any questions? Yeah, Denise has the hand up.
Oh, hi, Guillermo. Thanks for your very nice talk. I wonder, I think that at the very end, you said that you cannot yet reproduce the jets in planetary nebulae like the 7 709, because those are still protoplanetary nebulae. Yeah? Is that true?
No. I mean, the calculations are protoplanetary, very young planetary nebulae, without photoionizations. So now the next step is to include the photoionization and follow up those calculations to see which kind of planetary nebula will form in the future.
So the point is that you don't know instead, you don't know yet if the very narrow and fast jets are long-living structures or not. Yeah, this is the point.
Exactly, because probably the photoionization is going to break the circumbinary, it's going to evaporate the circumbinary disk. So probably once the photoionization starts, it's going to disappear the magnetic effect.
Okay. I wonder, I was trying to be completely sure about that. Thank you.
Okay, thanks, Denise. Adam, you had a question?
Yeah, these are beautiful results. Super interesting. So, comparing with the stuff that Amy did with our group and Ursula. So we have these very sort of cored apple configurations, and you end up in the end with very narrow up common envelope ejecta. And so I think that's something that we kind of need to work on more to understand, is this the fruit of initial conditions? If it's cooling how? Because of the, you would expect some mix of optically thick and optically thin. So I'm just wondering if you could comment on that. And then resolution as well, because you're tracking on so much larger scales, your resolution is going to be much lower than what we can do by just, with the AMR zooming in. But of course we can't go out and go look at the large scales like you can. So.
Yeah, cooling is important. As we talked already, nature always is cooling down. So we know that, for example, for stellar atmospheres, which is, we see the atmosphere of the stars. So below 10 to the minus 8, 10 to the minus 9, 10 to the minus 7, minus 8, minus 9 gray per cubic centimeter, everything is fully radiative. So the ejecta calculated in the common envelope solution actually are artificial because they use adiabatic conditions. For example, in the phantom or Paul Ricoeur calculations, the outflow that you see are below 10 to the minus 8, 10 to the minus 9 grain per cubic centimeter. So it must be fully radiative. So for example, in your case, all the flow that go to the polar direction is completely artificial because, it has too much temperature, the gas is trying to find the sphericity again, back, the sphericity. So all the solutions that you have in your computation are because you don't include the cooling.
But why will the cooling?
If you get a much thinner solution, and that's what we have to work. But the people doing the common envelope evolution has to include the cooling, because the ejecta that they calculate is artificial.
Well, except but the problem is that if you're expanding supersonically, the cooling doesn't matter in terms of you're not going to collapse down to the axis. If you're expanding supersonically, all the cooling does is lower temperature. It won't redirect. There's no pressure gradient due to gravity. You're expanding supersonically. The gravity's low. So that's why we're in this weird regime where we're depending on what your scales are, what your cooling are.
Yeah, but here depends on how much mass you have bound in the ejecta. In our case, 75%. So that mass is in Keplerian orbit. It's not expanding. So something that in Keplerian orbit, we know that if you radiate, it's going to be a thin disk. It's
okay,
like
I'm going to stop this question here, because this is maybe better for a discussion in the next section. I'm sure it will come up back up. Ursula, you had a question?
Do you want me to wait, Albert, for the discussion? Actually, I can say just one quick thing. As we go to more sophisticated common envelopes, so we go from adiabatic with ideal gas, and now, of course, we're using tabulated equation of state, which releases recombination energy and gives you ejection of the envelope. Now, of course, those are not great either, because being adiabatic, you can release recombination energy, but as Noam has said many times, you're making it do work when maybe it doesn't do work 100%. But the point is that the ejecta shape changes quite dramatically if you have this extra energy due to recombination. It's actually a lot more spherical than we've been used to in the past. So once again, we're doing all this, and then the whole common envelope ejection geometry changes under our feet. So I guess, Guillermo, you start again when we have the new generation of simulation.
Okay.
And we're cooling.
Yes, there has to be some.
Yeah. Okay, then can I now suggest that everyone unmutes themselves for a second and gives all the speakers some applause?